Before we jump into Newton's laws, I want to distinguish some of the key vocabulary that we'll be using. In physics, speed and velocity have subtly different meanings. Even though velocity does incorporate speed, it also incorporates direction. So simply, speed is a magnitude. It's a number that just represents a quantity, okay? So the speed is how fast an object moves. Totally normal with that definition, okay? Velocity is how fast an object moves. So it's got speed in it, right? And, that's why I underlined it, and in which direction, and I should put on here, in which direction it moves. Okay, so if I look at these two cars, if I look at these two excellently designed cars, I should do this for a living. Car 1 is traveling at 30 kilometers per hour going in this direction. Car 2 going 30 kilometers per hour that direction. So their speed is the same. You can say, yes, 30 kilometers per hour. So that's just a magnitude. It doesn't say which direction the car is going. If I now compare those speeds, I can say the speed of 1 equals the speed of 2. So their speeds are the same. But their velocities, very subtly, they're not the same. They have the same speed, so I can say the velocity of car 1 has the same speed as car 2, but it's in a different direction. It's going that way. Car 2 is going that way. So their direction is different. But they're equal in magnitude. They're the same speed. So velocity is a speed and direction. So it actually equals the negative of velocity 2. So they're not the same. They differ by a negative sign, even though they have the same speed. So that's just the concept of speed and velocity. So when we talk about orbital motion stuff, we're going to be talking about velocity, orbital velocity, things like that. We've discussed those terms a little bit, but now we're just going to define them a little bit more particular so that when we talk about Newton's laws, we can be a little bit more accurate. So that brings us to acceleration, where I have another beautifully drawn car. Okay? Now we're going to talk about acceleration. If I change the object's speed, that is an acceleration. If I change the object's direction, that's an acceleration. So a change in velocity is what an acceleration is defined as. So acceleration is a change in an object's velocity, and it can be either the speed, the direction, or both. So if I have just a change in speed, I've got an acceleration. If I've got just a change in direction, but I maintain the same speed, I've got an acceleration. Or I can change both speed and direction at the same time. Okay, and that's going to be an acceleration. So here's a little bit of an example. This driver is just traveling along the highway merrily, going 80 kilometers per hour. Sees the speed limit sign is really 70, and then sees a cop car. Now he's going to panic. I kind of like this little cop car. The cop is going to bust him if he's not, if he's still going 80 when he crosses in front of that cop car. Well, it doesn't really work that way. Cops already probably nailed him, but we're going to assume that he has to cross that line. All right, so this driver here is going to slam on their brakes to get down to 70 miles an hour. So he goes, or 70 kilometers per hour. So he goes from 80 kilometers per hour to 70 kilometers per hour. All right. During that time, while he was slowing down, or she, whoever is driving that car, by the time they came up to the cop, that driver was experiencing acceleration. Only during that time. After that time, it could be going 70 afterwards and maintaining a constant velocity at 70 miles per hour. But during that time, let's say it took 3 seconds to slow down. So over this amount of time, there was 3 seconds. So for 3 seconds, it was changing his speed, or the driver was changing their speed. And it was in that direction that they were changing their speed. That might seem a little counterintuitive because they're still moving in this direction, but the acceleration was in the opposite of the motion because they slowed down. So as it was coming in, it slowed down in the opposite direction. Some force, which turned out to be the brakes, we'll talk about force in a second, try not to use that term, caused it to change its speed in a negative direction. So like people will often use the term deceleration, which isn't actually a technically correct term. Acceleration is just a change in speed. So you might intuitively say he decelerated, but the truth is it was an acceleration, and the acceleration was in this direction. So we're going to call the acceleration A here. And so let's put here actually. So as he's doing this, his acceleration is in that direction. So his velocity is going, I keep saying his velocity, so fine, he's a male. The velocity is keep going in that direction, the acceleration is in that direction. That causes the change in speed, and therefore he's accelerating in the opposite direction that he's traveling. Okay, so let's talk about different kinds of acceleration. I shouldn't say different kinds of acceleration, but let's visualize a couple of different scenarios with acceleration. Now we've got this driver, and now he's obeying the law, and he's going 70 miles or 70 kilometers per hour. And so he's going 70 kilometers per hour in this direction. Comes upon a slow-moving semi. And the semi is going, we'll say, 60 kilometers per hour or something. We don't even need to worry about the semi for this part. But he's just going slower, and this driver wants to get around him. Now the driver, without changing speed, we'll call this path A. So during path A, the driver doesn't change speed. Kilometers per second. Or kilometers per hour, sorry. So he's traveling, he maintains that 70 kilometers per hour speed that he was already moving with, and he alternates his path and goes in that direction. There was a change in direction. So path A here, we'll call it, change direction. Same speed. You might think, didn't change his speed, there was no acceleration. But there was acceleration in order for him to change his path. So he changed his path, so he accelerated. And the acceleration was in that direction, towards where he was going, because his velocity was originally going in that direction, and acceleration caused him to move more in that direction, and his velocity moved in that, and you get a path that was diagonal, if you will. Trying to keep really simple terms here. All right, so now he's moving along, and he's uncomfortable being next to the semi. I don't like driving next to semis very much. It just seems like they can't see me. I can feel the wind bouncing me around. So I tend to speed up a little bit when I encounter this situation where I've got to pass a semi, personally. So let's say he speeds up back up to that speed he was before he saw the copper at 80 kilometers per hour. So in path B, he speeds up. So changes speed. But direction does not change. Sorry. Writing that really poorly. So, in this path A here, he changed direction, there was an acceleration. In path B, he changed speed, but not direction. Okay, so let me go back, step back. In path A, he changed direction, but did not change the speed. Was going 70 kilometers per hour, maintained 70 kilometers per hour. There was still an acceleration in that direction. Path B, when he gets on the side of the semi and speeds up to get around it, during that time he's accelerating up to 80 kilometers per hour, but he didn't change the direction. So his direction doesn't change, but he changes the speed, and you still get an acceleration. So so this goes back to velocity. I'm saying speed here on purpose to indicate that difference between velocity and speed, because the velocity is changing here because it's changing direction. The velocity is changing here because it's changing speed. Velocity is speed and direction. So I'm going to talk one more, and this is about one more case of acceleration, and this will kind of lead us a little bit into Newton's laws. This is more similar to what we experienced with planetary acceleration, because a lot of times the orbital velocity won't change very much, but its direction is always changing because it's always changing direction, right? It's in order to travel in a circle. If this object is just cruising along here, if I got a planet cruising along, it's going to go in a straight line unless something causes it to change its direction. So in order to go in a circular motion, it has to have an acceleration. We are going to get into Newton's laws, and this is obviously on gravity, so we'll be talking about gravity a little bit in a moment. So that's what the acceleration is. But let's go back to your everyday experience. And this driver is encountering some kind of off-ramp or some curve in the road in which this driver has cruise control on or something and still obeying the law, going 70 kilometers per hour and cruising around this bank. Okay, but the speed is not changing. So there's an acceleration though in order to keep because otherwise the car would just go straight. This would be the path with no acceleration. It would just go straight in a straight line off of the ramp and into trouble. Okay? It's a really bad drawing. I suppose the double dots don't help. So that's the path that you would have taken had you not accelerated. So in order to maintain a curve like this, you've got to be accelerating. And that acceleration is towards the center. So this is the acceleration is going in that direction. And this is the acceleration all along that curve. At this point here, the acceleration is going to be in that direction. At this point here, the acceleration is going to be in that direction. And that's because he's accelerating to change his speed every time, or change his velocity every time, even though he's keeping his speed the same. His velocity is changing its direction at every point along this path. And so that whole circular arc is an acceleration. This is what happens with orbital motion, is that there is an acceleration towards the sun in most cases, or with the moon, its accelerations towards the earth. And this is more of the type of acceleration that we'll be talking about in astronomy. I want to point out here what causes that acceleration. If you ever notice when you drive on a highway or something, that's an extreme bank. So if I'm going to draw the car from maybe behind or something, or from, right? That's another extreme bank. All right, let's just do this. Okay. So have you ever noticed that especially on highways where you're going a lot faster, you'll notice that the road kind of banks like that. That's a really fast bank. You have to go. This is like racetrack speed. Okay. Sorry, I tried to lower that, but every time I drew it, you just witnessed, couldn't do it. But the bank here is what is causing that inward acceleration, and this will lead us into Newton's third law later. But it's really the road is pushing on the car that way. The car has a weight associated with it. It's pushing on the road, and the road is pushing back, and that's what's causing the inward acceleration. All right, so these are just the basic principles. We're going to go into a little bit more detail in a second, starting with, so we've basically covered Newton's first law so far. So basically, Newton's first law is an object in motion tends to stay in motion unless acted upon by an outside force. So it continues at the same velocity. It's just rock in space. It just keeps going that same constant speed until something changes its motion. That's Newton's first law. So this, when we just talked about with acceleration, that change, an outside force acting on an object, causes a change in velocity, which is the acceleration. That's going to lead us to Newton's second law. So now I'm going to talk about Newton's second law. Newton's second law is one of the biggest things in our engineering world. Entire physics courses are devoted to Newton's second law. So you can have a quarter of introductory physics. If you take a course, the whole quarter, you're probably going to be talking about Newton's second law, and it keeps going and pervading through everything that you do on a non-advanced physics. And almost everything relates back to this in some sense. So Newton's second law is F equals ma. Well, what do these terms mean? Well, F is the force. I should have probably wrote that there. F is the force. Okay? the force, Newton's second law is saying that the mass times the acceleration is equal to the force. So before, when we had the car, we had to slow it down. We needed a force to do that. When we sped it up, we needed a force to do that. When we changed its direction, we needed a force to do that. Okay, so these terms in here, m is the mass. Do not confuse mass with weight. You're usually accustomed to the term using that idea as far as weight goes, but a mass doesn't change. It's the amount of matter an object has, and it's measured in kilograms. So kilograms there. So it's measured in kilograms. Now, the amount of mass you have doesn't change. On the moon, you weigh less, quite a bit less, like 1/6, I think, and therefore you see when the astronauts are walking, they're almost floating because they weigh a lot less on the moon. But their mass doesn't change. They haven't shrunk or anything like that. They just, the amount of matter that is in their bodies has not changed. So mass is a property defined by the amount of matter an object has, okay? The A is acceleration. So we just went over acceleration in detail. And this is a very, very quick talk about F equals ma. Rather than doing a whole course, I'm going to try to sum this up in a couple of minutes here. So what this basically says is that an object with greater mass, you need a bigger force to change its direction in order to keep acceleration, to put some acceleration. If you want to accelerate more, then you're going to need a bigger force in order to get more acceleration. So this is the concept of this basically is that the greater the mass, the more force you need to have an acceleration. The greater the acceleration, the more force you need. So if I have a greater mass and I want to have the same amount of force on that mass, I also need a greater acceleration. This is just basically just summing that up rather than making you go through detailed calculations of this. This is a very, very important law, and it governs how we derive other forces like the force of gravity, which we'll be talking about in just a little bit. But for now, all you really need to know is what mass is, what acceleration is, and that force equals mass times acceleration. So now we're going to talk about Newton's third law. Newton's third law is, people love this phrase. This is a very, very popular pop culture phrase. This happens to be a very important law of physics. For every action, there is an equal and opposite reaction. What does that mean? Well, if I push on this board, I feel like the board's pushing back. Otherwise, my arm would just go right through, right? But I'm applying a force to the board, and in order for me not to fall through, in order for me to feel the force in the board also has to be putting a force on me. Similarly, I'm standing on the ground. I don't fall through the ground because something else, my weight, is pushing down onto the ground, and the ground has to push back up to balance out that equilibrium. So just schematically, here's the force of my weight, right? And then here's the force of the ground. These are equal but opposite, and that's why I can stand still. I am not going upwards. I am not going downwards. These forces are exactly balancing out. And this has very important properties for implications of space travel and how this works in space. Now, we have an atmosphere here. We're right at the surface where there's a strong gravitational field. So we don't quite experience this. But let's just say I have an astronaut in space, and he's got some kind of ball in his hand. Okay? So this astronaut's just floating around there happily. He's just holding the ball. And he decides to throw the ball. So he throws the ball this way. And this is at some later time. The ball has left his hand. And now he's over here without it. No more ball. Doesn't really have a hand in the first place. Kind of funny looking drawing here. Give him some boots. Okay, so he throws the ball now, and the ball went that direction. And the ball is traveling now at some velocity v. Okay? he also, because of equal and opposite reaction, right? So he applied a force that direction, and the ball pushed back on him, okay? So this guy who is floating free, where his V naught, that usually the little zero is V initial, V at time zero, his V naught was zero. But now he's got an equal velocity, not equal, sorry about that, but he's got some velocity in the other direction. This ball weighs a lot less, so his velocity is going to be a lot less than the ball. So actually, let's get that straight here and make these values somewhat a little bit more proportional. So this is what would happen if you threw a ball in space. You would go a little bit backwards. So if you're watching a sci-fi movie, sometimes they might even use that property where they cut something, or they do something where they throw something in one direction to go the other. But a lot of times sci-fi movies actually get that wrong. So basically, for every reaction, there's an equal opposite. So he applied a force, but he also had an equal and opposite reaction this way. The reason why his velocity is less is because his mass is larger. So it's much harder to accelerate someone when their mass is larger than the ball, which is easier to accelerate. But the forces were equal and opposite in the magnitude of the way of the direction. Their magnitude was the same, but they're opposite in direction. So there was a action and there was an equal and opposite reaction, causing now this astronaut to change his velocity in that direction after throwing the object or the ball or whatever it was. So this has really important implications in the limits of the speed the limits of the speed of our spacecraft. So we are limited because we don't have anything to push off of. If I'm driving a car, my wheels are pushing on the ground. If I am running, my feet are pushing on the ground. So we have something to push off of. That's essential. Airplanes are pushing off of the air. They're moving the air one way, which is causing the plane to go another way. So you need something to push off of, and in space you don't have that. So just like the astronaut example with the ball, that's kind of the same thing if I have a rocket, which I didn't plan out how I was going to draw this rocket, so that's a really ugly looking rocket. Okay, so the rocket exhausts some kind of fuel this way, right? And rocket fuel, you're going to be rocket scientists for a moment here. Rocket fuel is usually some mixture of water and other water and some kind of other liquid molecules, and it exhausts it by doing this. This is what actually gives the rocket in space the acceleration. On Earth, it has the atmosphere to push off of. It's got something to push in order to push it in the other direction. So what happens here is the exhaust velocity, let's draw this vector, goes this way, and then, so this is from, I'll just call it the exhaust, and then the rocket velocity goes that way. Okay, so that might seem a little bit strange to you, but this is what limits our space travel, our ability to travel faster, is that we are limited by how fast we can exhaust our material. So it's usually more of a solid, so we burn it, and then it gets high pressure, and it ejects out the back of the rocket, and then that rocket will then push, by the equal and opposite reaction, pushes the rocket forward. So the limits of our actual spacecraft, by using these types of engines, there's all sorts of work on new engines, but they're not so good or efficient enough to avoid having to do this. This is still the best model we've got. They're still limited by how fast they can eject that fuel. So our top rockets can exhaust the fuel at something like 15,000 kilometers per hour, but that limits how fast the rocket can go. Even with a small mass on the rocket, it's limited by how fast it can exhaust the fuel. So that's Newton's third law as it pertains to us, which is a very, very important law in regards to why we don't get to visit other planets. Finally, we get to talk about gravitation. This is a consequence of Newton's second law, F equals ma, and it's really important for planetary orbits. We studied Kepler's laws last week. Kepler's laws, they travel in ellipses, and the planets speed up when they're closer, slow down when they're further away, and this has to do with gravitation. So Newton was able to put this all together, all that work from Copernicus, Brahe, Kepler, Galileo. He was able to put it all together and came up with his universal law of gravitation. I was going to start with this, but now I just thought about something else here. This is what Newton conceptualized, okay? Newton had thought about the Earth. And you take a little cannon here. So I'm going to have a little cannon. And the cannon shoots a cannonball, okay? Eventually falls to the Earth. Can you see that really? Let's draw this bigger, because this is kind of a really cool concept. This is kind of a good way to understand some things. So you're on the Earth, a really huge cannon up here. Cannon fires a cannonball, travels for a little bit, hits the ground, okay? What Newton conceptualized is, what if an object can go so fast that it can go, what if you can have a cannon that fires the ball so fast that that ball travels, the cannonball is going so fast that it goes all the way around before it hits the ground. This is kind of what you get with an orbit. It's going fast enough so it can't fall to the ground. It's really poor description, but you will have to work with it right now. But this is what Newton conceptualized. So he started to understand how these objects in the sky work together. So here I've drawn two objects of mass 1 and mass 2. We'll call this would be like two asteroids or something, that far apart. Their distance are apart. Okay, the gravity acts towards the object. It's always towards the object, which is kind of weird versus other things in physics, but it's actually more intuitive to us because we experience it all the time. So it's always towards the object. So these objects are going to mutually attract each other because they're pulling on each other, essentially, because this one wants to pull this guy wants to pull this guy. Okay? Now what happens is, I'm going to try to double this distance. So now I've doubled the distance. So I call that an initial distance r, and now I'm going double r, which looks like about here. Okay? Now that attraction is less. So that's less than that. We'll get into that. So I'm just going to, again, triple it, and now we'll talk about why I'm doing this. Okay, so that's mass 2. So now that's 3 times the distance. So what happens is, it falls off over r squared, which, if you're not a math person, you're like, what does that mean? So let's just write out what Newton's law of gravitation is. So it's F equals, this is a constant, so this is a constant of nature, which in some sense is related to how we choose our units, but we're not going to get into that. So F equals m1 times m2, so the masses of each other times over the distance squared. So this distance r squared. So if I put a bigger number in here, what happens to the quantity of force, which I'll call F of g? What happens to the force of gravity? It'll get smaller because I'm dividing by a bigger number. So the bigger the r gets, the bigger I'm dividing it by. So here, it's just simply F of g equals, this connects to that one, right? So if I put in 2r, what I have done here now is I'll have force of gravity equals 1/2, or no, that's even wrong, 1/4. 1/4 because I took the r squared. Let's just be explicit here. Let's go from this one here. Let's look at this one, and let's be explicit. So the masses haven't changed, same masses. Now I've got 2r squared, so I've plugged that into there. And so I get equals 1/2, or 1/4, I did it again. Amazing. 1/4 g times m1, m2 over r squared. Okay, so this is the same quantity as this is, but by moving it, by doubling the distance apart, that magnitude of that force, I reduced it by 1/4. So the further away you get, the weaker the force of gravity between the two objects get. So let's just really carry this on here. and go on to this other one, this other example, where now I have a distance 3 times as much as the original. So r was the original, and now I've gone 3 times the amount, 3 times the amount of the original distance. This is 3 times longer than this is. That was 2 times longer. We reduced it by a fourth. Now we end up with 1/9 of that original quantity. So I'm calling this the original quantity, which is this, which is this. So you can see as you increase the distance between the objects, and am I kind of off the screen, or I'm kind of off the screen? When you increase the distance of the objects, initially you have, like, say this, if you're calling this your initial distance, and I've circled it, but you can't really see the circles, can you? I've circled that quantity. So now if I change that and double the distance, I'm squaring it because it's in the numerator, and I'm plugging that into here, and I'm squaring it. So I end up getting a 4 out of here, but I still have an r squared, just like I had an r squared up there. So I just factored that out. I'm not going to ask you to calculate a lot of these. I'm trying to give you a good conception. If you don't see that automatically, just take my word for it that you get a 1/4 times the original quantity. Okay, so that's why I circled this. Original quantity, original quantity, original quantity. If you go 3 times that distance, you plug the 3 in there, that becomes a square, that becomes a 9, so you end up with 1/9 times the original quantity. So the further you get away, it drops rapidly. So it drops exponentially, as we'd say, the further you get away from an object. So when we were talking about Kepler's laws, when it was closer, it was moving faster because the force of gravity was stronger. But when it got further away, especially in elliptical orbits, it really slows down when you get really far out. Unfortunately, we didn't have the example of Halley's Comet, which was really nice because it speeds up and slows down drastically. But there was a result of this because the force of gravity falls off the further it gets away, or the further the object is away from what it's what the other object is with mass. Okay, so with that in mind, this kind of summed up why Kepler's laws operated the way they did. And the force of gravity has effect on tides and stuff, which we'll study a little bit in the reading and in the homework. Interestingly enough, let's talk about the tides for a moment, even though this composite of this whole video is going to get really long here really fast. So let's just clear up some space here. Okay, let's talk about the tides for a moment, because this is kind of an interesting thing here. So I've got the Earth here, and the moon causes it to bulge as it rotates around, so it squeezes it a little bit, and the moon becomes, or the Earth becomes a little bit elongated as all that stuff is attracted to the moon. It causes the tides. Okay, so initially when there was a brief little bit that you might have saw in the reading where the moon was receding over time due to this tidal interaction that was going on. So the moon was actually at one time much closer. So by being closer, thousands of years ago, the force of gravity was greater than, let's call this force of gravity in the year, I don't know, let's say like 1 million years ago. 1 million years ago. So the force of gravity 1 million years ago from the moon was much greater than the force of gravity today. We'll call that force today. Sorry, this is impromptu, but I really think this is a really interesting thing to picture. The moon was much closer, so it created much bigger tides. Like whole valleys would get flooded with enormous amounts of water throughout the day and night when the moon would pass over and pull on all the water that was as it was going around it. Okay, but millions of years ago, when the Earth was much closer, or the moon was much closer, that effect was much more dramatic. Over time, this is drifting out into space at a couple of centimeters per year, but over 1 million years, that actually adds up. I used to ask that in a quiz question. Maybe I'll do that. So the moon continued to recede, so now it's much farther away, so now it's actually much less of an effect. The tidal effect is a lot less, and that's due to what we were talking about here before, where the force of gravity, without explicitly writing it again, the force of gravity was proportional to the 1 over the distance squared. So it used to be a lot stronger, and it's getting less and less each year. So that's just something fun to picture. And if you can imagine yourself traveling back in time, millions of years ago, dinosaur era, whatever, you look up the moon and it's going to look a lot bigger because it's a lot closer, but the tides will also be a lot stronger.